Furthermore, can this tool unify the different data management alternative databases, basically? So the users need not be concerned. The user needs not be bothered by how the data is stored or how it's managed. And what we propose to solve this problem is create a data service, basically. This data service manages the data for the user. And it does this depending on categories and keywords. It also works with different types of databases. Could be SQL databases, non-SQL databases, NH-based databases, or other type of paradigm databases. And it has to be modular. Why? Because every time a new research institution wants to be part of this data service provider, it might be a different type of database. So it doesn't need to, we don't need to adapt the whole system to be able to join this new database instead of just being modular, just like next module that creates more functionality. So an architecture. So this is our architecture. We have a user on the top, that is the person that wants some type of data. A data service that it manages the query and the data providers and the data providers. So the user API is basically a search engine where you put what you want depending on keywords and categories. The data service itself is the one that manages everything. It transforms the data, the query, so it becomes meaningful to the system, and the system then gets the data. And a way of registering new databases providers. So we are using Java for this implementation. And we have servlets, we have Ajax, JavaScript, and right now we support MySQL and H-based databases. So as an example or more general view of this work, say for example we have these two tables. One is MySQL and one is H-based. So the first thing is you have to register those tables. So you go to our service, you fill the information, you register, then you do the same for the other two. And they sit here in the database providers. So they are ready to be used to. So someone wants something that is inside those tables, you just can get it. And there you go. So someone wants a type of measurement. So radiation measurement. And you convert that to a meaningful query using our search engine, which is the user APIs. But what's the problem? The databases, they speak different languages. That's why one is SQL and the other one is HBase. So we need to transform this higher level query, which is I want something, to something that understands, the databases understand. And as I know, for example, for MySQL, it's a relational database. It depends on rows and columns, and the queries are more intuitive. Whereas the H-based databases are depending on families, attributes, and qualifiers, and they are not intuitive. So that means they speak basically different languages. So you have to have a translator to translate basically to those. So say we solve that. And now we are going to get the data. So, and you go at it. Say you get the data, and then you finish your table. You aggregate it. But what? It's like really slow. It's like sequentially. It's the case that works, but it's just not the best. So can we do better? Let's do it in parallel. So how do we do this in parallel? We have different ways of doing it in parallel. So the first way we tried was doing it one thread for each database. So as we see in the table, both tables are going to provide the data sequentially. So what happens when we did this? When you have more entries in your databases, it actually becomes slower. So your parallel algorithm is slower than your sequential. And that's really bad, right? Parallel is faster. So as you go more entries, your performance goes down. So this means it doesn't scale. So our first idea of doing in parallel became to it like a huge effort to get it done. Bravo, it didn't work. So we said, okay, it's still parallel. There has to be a way of doing this that actually makes it faster. So we say, okay, instead of using each thread for each database, we can divide the data inside the database and use threads to put the data in the table. So for example, say I divide my tables using 3 rows or 3 entries for each table. And then I add them in parallel. That would be a way. You can also divide the table in 2 entries per thread and do the same. So we did this, and then we find out that it actually works faster. And for this, I have 2 cases. One, when you had 10,000 entries for each table. And as you can see here, when you divide your tables using 20 threads, so 10,000 divided 20, so that's like 50 entries. Each thread manages 50 entries. You get around 6.5 improvement. When you go to 10,000 entries, the improvement goes higher. So that means right now you can even get 50 times faster than your sequential approach. So if we look at the execution times, as we have more entries, the parallel version of the algorithm works faster as expected. So now it means it scales, which is great. And the performance also grows exponentially, which is also very nice. So that of doing in parallel right now. So okay, so as I mentioned earlier, I'm with the OSDC. So we want to use this to help the OSDC. And the OSDC is an open science data infrastructure that allows users to have access to data cloud resources like machines and memory and all that. So we want to use our data service to provide the data, basically, that is going to be processed using the OSDC. So that's an extension of the work we're doing now. So for our demonstration, so this is our service. Good.
Yeah.
So okay, right now there's a way of registering the databases, as you saw. You just fill the form, you submit. There is a way of also seeing which databases are currently supported. So right now we have those. So you have information about the databases locally in the world. So that's nice. And okay, so for the query part, so say for example, as I said, say you want radiation, and then you want some measurements of that radiation. So these are some made-up tables. So you get information from 3 tables, basically, one that has this information. And if we go back to the initial case, when you have more information, you can have better research results. Because if you take out information that you don't know, you might think that somewhere here you don't have anything. But in reality, you do have it. And it might be relevant when you add it, as you can see. So that's a contribution of our work. So back to the questions. How can we create a tool that allows users? We create a data service that pretty much does that. Gets data in a way that the user can be more happy with it without even worrying where it is. So just, I want this, and he gets it. Can this tool unify this data? Yes, it can. We just need to be a translator between the different type of databases that exist. So some conclusions and future work. So the data discovery that we get is challenging doing this because when you talk about data might mean something for some field and something else for another field. And it might be the same. For example, if you think of coordinates in astronomy are not the same coordinates in geology. But when you go to the engine and you tell the engine, I want coordinates, then you have to be, the system should be able to handle that and decide what is exactly what you want. So that's one of the challenging parts. The parallelization, as we saw, works better when you divide the data instead of dividing the databases to do in parallel. It's just better to do that way. And as a future work, we're going to work on the semantics part of this to decide a better way of querying the data and the databases, basically. So that's it. And before you start with the questions, I would like to thank you thank SNE for having me. It's been great. You guys are really nice. I really enjoyed my time here, and I hope you do great things. I'm sure you will. So right now, okay, you can ask questions.
Okay, so other questions? I would have a question. So in your 1 or 2 slides back, you start
No, it goes
forward.
forward.
So here, your middle part more or less describes method use and flow.
Yeah, you could say that. And you could also say that, yeah, I mean, it's the way it works. For example, when you do GPU, also what you divide is the data, basically. So, and it works that way. So we can say that it has that approach. And now that you talk about MapReduce, H-based databases they rely on MapReduce. So that might be a consequence of why it also works. Yeah.
Can you give some remarks about where your radiation data was coming from?
Oh, no, we just made that data. We just, yeah, exactly. We just.
So not measured outside.
No.
Other questions?
Regarding the data integration or aggregation, did you try to use already existing tools, for example, Square, that already support a lot of data? Maybe most of them are relational, but the idea would be, for example, to extend it.
Yeah, exactly. The idea is to create the service because it's not really something that you can find easily. Because as you say, okay, there might be some that do for relational databases, but when you include non-SQL databases or HBase, which is not relational, it's become difficult. So we didn't try other services. We said we were going to start out from scratch.
Okay, thanks.
Combining information from different sources, do you see any problems that like the data can be recorded with different assumptions?
What do you mean, like? Okay, yeah, the data is coming from different sources. Like right now, okay, this is a made-up sample, but if you think, for example, genomics data, you have the PDB, the protein data bank, and they have other data, but there are other institutions, so it's different. So that's what you're saying, right? Combining it becomes challenging because exactly you don't know how is. You have to be careful in each case to get it the way they provide and somehow put it together. It's like a translation, basically. Translate it from all of them and put it together in a way that you understand it.
Yeah, but the data can be recorded with different assumptions in mind, or that the experiment was a little bit different. And
Yeah.
data together can be lectures.
We really don't care about how the data was generated. That's part of the problem of the scientists that generate it. So if he was a chemist or something and he generated it in a way and then he tried different way, we pretty much don't have control over that. When we put it together, we just assume it's good data.
But it should be meta-analysis.
Yeah.
Yeah.
Information and it's essentially
Oh yeah.
all of this stuff should be meta-analysis.
Okay, but I was thinking maybe you could test that the data sort of has the same distribution, therefore it could be from the same source.
Yeah, we that's the next part. Now that we have the system pretty much set up, now we can go and this is where the OSDC comes from. They have some data sets that are real data sets, and then we can try all those things that you're saying. Say pretty much those tests with real data and see if it actually does the job it's supposed to.
Okay, any other questions?
I have one more question.
Oh, sorry.
How, how schema dependent are you? Because you now have your X and Y coordinates, but I can see that some research
It might be
would
different.
tend
Yes, that's the
behind
challenging
it.
part of the problem. So yeah, in a way, that's something we are working on now, deciding how that's going to be done. That's the semantics part and also some work about the schema because yes, that's right. It might, the naming might be different, although they mean the same. So on a schema would be in a way of the schema part. We don't want to do like create a single way that you have to accommodate to that. We better accommodate to you instead of you accommodating to us.
Yeah, but putting things together, then at a certain point you have one thing and one thing, you somehow have to glue them together.
Exactly.
Yeah.
That's something we're working on deciding